Okay, so we're going to continue our discussion of limits. And so we found out in that first lesson that sometimes the value of the limit and the limit are the same number. And that's when the function is continuous at that point. And so when that happens, we said we could just plug in the value. So today we're going to discuss different things that you can do to determine the limits without the graphs. And the first one is just to plug in the number. So we're going to just try plugging in the number. So this says find the limit of f of x equals x minus 5 when x approaches negative 1. So let's practice writing that as a limit first. It would be the limit as x approaches negative 1 of x minus 5. And so then we could just try plugging in negative 1, and we have negative 1 minus 5 would be negative 6. We know that this is an equation of a line. We know that a line is continuous, and so the limit and the value would be the same. All right, so let's look at example 2. It says find the limit of f of x equals x over x minus 1 as x approaches 3. So again, let's try writing it. The limit as x approaches 3 of our function x over x minus 1. So this one is not necessarily continuous. We know that this has an asymptote, a vertical asymptote at 1, but the 1 where the vertical asymptote is located is not what they're asking us about for a limit. The limit they're asking about is at 3. So we probably will be okay here in just plugging in the values. 3 over 3 minus 1 is 3 halves. Now I do want to try to talk a little bit more about that one in the graphic form, just so we're clear. We know that we have a vertical asymptote at 1. The coefficients in front would give us a horizontal asymptote at 1. And so this graph ends up being a rational function graph that looks similar to this. And so 1, 2, 3, they're asking us about the output value at 3 right in here. And so that value exists, and so does the limit. The limit would be the same as whatever the value is, because it's continuous at that point. Okay, so the next problem, I'm really hoping all of that was showing whenever I was working. I think it was. Okay, so on the next problem, it wants us to find, it says if f of x equals x minus 2 over x squared minus 4, find the limit as x approaches 2 of f of x, and the limit as x approaches negative 2 of f of x. Well, you can probably see pretty quickly that I can't put 2 in here. 2 squared minus 4 is going to be 0. So plugging in is going to be a problem. Plug in is a problem. We can't do that. So other than graphing, what else could we do? Well, here's what we're going to try. Let's write that first one. The limit as x approaches 2 of x minus 2 over x squared minus 4. Well, the first thing I would do is try factoring. Try factoring. Because if I were to factor this denominator, x minus 2, x plus 2, then the x minus 2's would reduce, and I would get 1 over x plus 2. Okay, well, if the reduced form is 1 over x plus 2, then my asymptote is now at negative 2. Right? The vertical asymptote for this function would be x equals negative 2. So positive 2 is no longer a problem. Positive 2 is just a hole. And we know from our work from yesterday that a hole in the graph does not mean that there's not a limit. It just means that there's no value at 2. no value at 2, but there is a limit at 2. I'll just plug in, and now we get 1 over 2 plus 2, or 1 over 4. All right, so now for the other part of this problem, we were looking for the limit as x approaches negative 2 of this function. And we could x minus 2 over x squared minus 4, we could do the same thing and rewrite that as 1 over x plus 2. But when I put in negative 2, I still get 1 over 0. And you can't divide by 0, so that's not possible. So it's looking like that this doesn't exist. So I'm going to show you the graph of it so we can kind of justify that it doesn't exist. According to our factors here, we're going to have a whole at positive 2 and an asymptote at negative 2. And the numerator was smaller than the denominator, so the x-axis is your other asymptote. And so your graph is going to come along kind of like the parent function graph shifted over, but it's got a little hole in it right there. Okay, so the hole was our first limit. And we know that approaching from either side, we're still approaching the same value, which was 1/4. But the second limit was at negative 2, and just like we talked about yesterday, when we look at the graph, on one side we're going up towards positive infinity, the other side towards negative infinity. They're not approaching the same thing, so this limit does not exist. All right, so for these kinds of problems, if plugging in causes an issue, we're going to try factoring. All right, and I just marked right through that so we couldn't see it. All right, so try factoring. All right, the next one wants us to find the limit as x approaches 1 of this. So the limit as x approaches 1 of x minus 1 over x squared minus 4x plus 3. I'm sure that will factor out. Let's see, we've got x minus 3 and x minus 1. And the x minus 1s are going to go away. So it reduces down to 1 over x minus 3. And so once I have factored, I can try plugging in my 1. I will get 1 over 1 minus 3, or negative 1/2. So the limit as x approaches 1 in this function would be negative 1/2. The other limit they want us to find is the limit as x approaches 3. And so if I use that factored form again, and the 1's go out, so I have 1 over x minus 3. And when I plug in 3 this time, I get 1 over 0. And there's really nothing else that I can do with that. So as we saw in the problem above, whenever that happens, I'm sorry about that, you couldn't see what I was doing. So same thing, the x minus 1 divides out. We have x minus 3 left in the denominator. Plug in the 3, we get 0. And you can't divide by 0, so this is not possible. So the limit does not exist. This one is also at an asymptote. All right, so far, this is kind of a confusing little chart down here, but what it's saying is that the first thing we want to try is to plug in. If plugging it in doesn't work, then you can factor. That's what we just did. So we could try that. This one we have not tried, so that's what's on the back. That's what we're about to look at. And then, of course, we can always use a table or a graph if we have a calculator or a function that we can graph. And we could determine that way. So after we factored, we learned that after you factor, we go back to plugging in. But plug in, doesn't work, try factoring. And after you factor, try plugging in. Then if it doesn't work, it just doesn't exist. All right, so let's talk about this multiply by conjugate thing. So on the back, they're asking us to find the limit as x approaches 9 of this function. It's a rational function, but it's also got this root in it. And when I plug in 9, it's not going to work. It's going to give me 0 in the denominator. And so this is where I'm going to use conjugates. And so what we want to do is multiply by the conjugate that of the where the root is, conjugate in this case of the numerator. So we're going to have the limit as x approaches 9 of 3 minus square root of x over 9 minus x, and we're going to multiply that by 3 plus square root of x over 3 plus square root of x. Now, the conjugate is what you would multiply by so that the inner and outer terms go away. So if I multiply these two things together, I'm going to get 3 times 3 is 9. Inside term and outside term are going to zero out because this is negative 3 square root of x, positive 3 square root of x, that's 0. And then square root of x times square root of x is just x, so minus x. And we're not going to multiply on the bottom because it will be more helpful if we leave it alone, because look what happens now. Now, the 9 minus x will divide out, and I have 1 over 3 plus the square root of x. So now, after I have multiplied by the conjugate, now I'm going to go back and plug in. So I'm going to plug my 9 in to this. So 1 over 3 plus the square root of 9 is going to give me 1 over 6. Right, so conjugate of the term with the root in it. And all that means is just change the sign in the middle, because that will cause the inner and the outer terms, when you multiply together, to zero out, getting rid of the root. Okay. So let's try number 6. So this time the roots are in the denominator. That's okay. We're still doing the same thing, except this time to the denominator. First of all, we do want to just check. Can I plug in the 2? No, because it would be square root of 2 minus square root of 2, which is 0. So that's when we're going to multiply by the conjugate of the denominator this time. Okay, so we're going to leave that numerator alone for now. And we're going to multiply the denominator. So square root of x times square root of x is just x. The inside and the outside terms zero out. Square root of 2 times square root of 2 is just 2. So we have x minus 2. All right. We still can't plug in the 2, and we can't just cross these out because they are not exactly the same. But to make them the same, I can just pull a negative 1 out of this numerator. It would become x minus 2 instead of 2 minus x times the square root of x plus the square root of 2 over x minus 2. Now we can reduce. We have negative 1 times the square root of x plus the square root of 2. And now we're ready to sub in the 2. So we have negative 1 times the square root of 2 plus the square root of 2. And those are just 2 square roots of 2. So negative 2 square root of 2. All right, so just to recap, back over here in this little chart, now we've done this side. We tried plugging in, it didn't work. So when it's got roots in it, you might want to multiply by the conjugate. After you've multiplied by the conjugate and reduced it down, then go back and try plugging in again. So, this would be your second step or third step, however you want to look at it, depending on the kind of problem. So this is always first, then try one of these, whichever one applies, and then go back and plug in. If after you've done these things it still doesn't work, it still gives you a zero denominator, then the limit probably does not exist. You might want to try the table of the graph to reinforce your conclusion.